Welcome, ladies and gentlemen. We're talking today about graphing sine and cosine functions. All right, where the angle we input will end up being the x coordinate of the point, and the output of that function will be the y coordinate of that point. And we'll end up having some very interesting results. But first, before we even get there, I've got written down here, which you don't have to write down, what a periodic function is and what a period is. So a function is periodic for some real number alpha if f of x plus alpha is equal to f of x for each x in the domain of f. So let me explain what that would look like. Here we go. Arg. That was a terrible. So here's like a y and x-axis. All right, so this is an example of a periodic function. What if I had this? And I just went like Charlie Brown on this graph.
I thought you were going to say Charlie Sheen.
Nope. Oh. And this graph continued infinitely. This function would be periodic because, notice, f of x plus a, or alpha, is equal to f of x. Notice for this point here,
Pickles.
Over here is the same point, right? Pickles. And it is alpha units away. And that alpha is the same alpha from this point to this point. Alpha units away. All right? So it's periodic because it's repeating a pattern horizontally. All right? And it could be mapped onto itself if I was to shift it over by alpha units or 10 alpha units or whatever that would be. So now notice, why isn't this the value of alpha right here? Because those are the same y values, right? Like that's the same height. But what's the issue? This
they're on the opposite side of
right, here's an alpha. So this point corresponds to this one, and this point would correspond to this one. Right? So it's not just the fact that it hit the same y value multiple times, but the whole graph is repeating that, right? And this point and this point were not kind of correlated with the rest of the graph. Calm down, friend. Calm down. I told you didn't have to write that down. You would have saved so much time. Listening.
Ankle bird!
Okay. So the value, the least positive value for alpha, for which f of x is equal to f of x plus alpha, is the period of the function. So yes, I agree that these two are a set distance apart, and if I repeated that distance, I'd actually land on another spot. But I wouldn't call that the period. The period would be the least value between those two. Okay? So that's what the period would be. So alpha is the period in this case, that it takes the pattern to repeat itself. Okay, so this is an example of a periodic
Those are some really bad squiggly
function. Yeah, it's okay.
I disagree.
All right. So this is the idea of a periodic function. It's kind of horizontally repeated, and the period is the distance, the smallest distance between those repetitions. So let's think about what would kind of another cool. Let's actually have you guys draw a periodic function, and then I'll end up drawing one of yours. So make up a periodic function. See if you could. Bless you. You don't even have to label your scale. I'm just looking for a periodic function. So draw one in your notes, and then I might copy one of your guys down.
Does it have to be straight?
No, it doesn't have to be straight. It could be all curvy. Anything that's periodic. Drawing pictures.
How do you make it tricky?
That's not periodic. Because it doesn't map back onto itself. It'd have to be kind of a repeated pattern.
Oh, mine's not repeating.
I saw some people with one like this.
Hey, that's mine.
Dylan, that's mine.
Now, however, this is periodic, but it's not a function. Why?
Because it goes backwards.
I think I know what you're describing by that, but could you be more
Yeah.
clear?
Please. Those like things that you like backtrack.
All right, this backtrack part, okay, horizontally speaking, it fails the vertical line test. All right, but it is periodic. Actually, I could even have
I have a chair.
a curly brace function
I have a chair one.
if I wanted.
I have a chair one.
A chair?
Chair.
What do you got?
Like chair.
But it doesn't
It
look
don't
like
look
that
like this.
pattern repeats.
No, but it does repeat.
So something like that would be periodic. If you wanted, well, your chair thing wouldn't quite work.
What?
I mean, I could even have something like this.
It would work. How would it work?
This green function would be periodic. Does anyone have another idea of a periodic function?
I do not know. Straight line.
Just a horizontal line,
Would be creative.
right? That would be periodic. What would the period of the straight line be?
One.
The smallest value would be this smallest number you could think of. Not 0, I suppose. Yeah, huh, that's interesting. That is a weird one. Yeah, an infinitesimal is what we talked about in pre-calculus today. Good stuff.
Pre-calculus. Is the best
But yeah, you could even have like a and then oh.
You're like me. You're like me.
Then it
I
messed
make
up.
sound effects when I play video games, like Grand Theft Auto.
Right, and then it would repeat. So anything is any of those would be periodic. And what if I wanted to find where this point occurs again? What's the period? Would that be over here?
No.
Would that be over here?
No.
No, it would be all the way over here. So to calculate the period, I'd have to find out how far is that, right? So these horizontally cyclical functions are periodic. So what we're going to do next, it turns out that sine and cosine are going to be periodic functions. Actually, why do you think sine would be a periodic function? We don't even know what it looks like yet.
Because it's
Oh.
It's a ratio?
Well, it's a ratio. And so sine of 30 degrees is equal to 1/2. When is sine equal to 1/2 again? 360 degrees later. So it's occurring
390.
at 390 degrees, right? It would land on that. But doesn't it also equal 1/2 at sine of 150 degrees?
I said that.
No, I said that.
It's true, Justin.
However, our concern would be, could that be one of these situations where sine is equal to 1/2 in both of those locations, but that's not actually the period. So we'd have to find out some more about it. But sine is periodic because of coterminal angles, right? If my angle is going to be my x input, there are technically infinitely many angles that I could plug in, but that pattern is going to repeat every, say, 360 degrees, or every 2 pi radians. So let's actually graph. Let me do this. Let me grab a snapshot of this. I'm going to get a snapshot. Ba-da-ba-ba. Now, we talked about that sine inverse had limited inputs to it. Do you guys remember what those inputs were? You couldn't plug in a
They
number.
can't be between, or they have to be between 0 and 1, or -1.
They had to be
And 1.
between -1 and 1. Let's see, did this work? Here we are. Blam. This is the only way I could fit my graph. Oh, that's so sad. I just want it to fit and have the radians. So check this out. So I've got my possible range is going from -1 to 1. And my x-axis is measured in radians. So pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, 4 pi over 3. So they've reduced these fractions for us. And I'm going all the way out to 2 pi. So I want you to draw this as well. Actually, where would pi over 4 be on this? Here's pi. Let's think about this. Here's pi. Half of that is this. And half of pi over 2 is right here. So there, I do actually have pi over 2 here. Man, green was the worst color. I need to choose something darker. Right, so here's pi over 2, and half of that would have been pi over 4, right? Right. So, so we're going to graph y equals sine of x, or f of x equals sine of x. And that's why I'm going to have to super awesomely know these values. Now, we could make a table of values. Actually, let's do this. So I'll have x, I'll have y, and we're going to plug in inputs of 0, plug in pi over 6, we'll plug in. Do you want me to plug in? I should plug in pi over 4. But I just want to point out pi over 4 is not the same increment as the other ones. Pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4 is another one that I should get. That's the same as 135 degrees. That one lands in a funny spot. And then 5 pi over 6. And then pi. Maybe that might be all we fit, but we'll represent the rest of the graph here. So what is sine of 0?
1. Sine of 0
is 0.
I was right.
Yep, you were right. You were right. You didn't sound confident though.
Oh.
What is sine of pi over 6? Pi over 6 is 30 degrees, so 1/2. You're allowed to do the hand trick. Sine of pi over 4? Root 2 over 2, right?
Oh.
Sine of pi over 3? Square root of 3 over 2. Sine of pi over 2? It's 1. Okay, so that was all in the first quadrant. Sine of 2 pi over 3, that's in quadrant 2. Sine is still positive in quadrant 2. And what is the reference angle of 2 pi over 3? Well, it'd be 180 minus that, or pi minus that, or 3 pi over 3 minus that. So the reference angle is pi over 3, I believe. Pi over 3. The reference angle here would be pi over 4. The reference angle here would be pi over 6. And we already said that those were positive, so it should repeat some of these values. So this will be root 3 over 2. This will be root 2 over 2. And this will be 1/2. And what's sine at pi? Sine is 0. Right? Because sine is the y-coordinate on that unit circle as we're going around. So let's actually plot some of these points. So yeah, draw your y-axis from -1 to 1, and try to fit all the way over to 2 pi. And actually, let me show you. I'm not going to leave this here, but when I do that, I'll do this. I'll go out to 2 pi, is what I'll do, and then I'll cut that in half and mark that as pi, and then I'll cut that in half and mark that as pi over 2. All right. And then you could cut that in half and mark that as pi over 4, I suppose. And then this would be 3 pi over 4. Right? This would be 4 pi over 4, and then 5 pi over 4, I guess I'm technically labeling this a little bit different, but I could have also divided by 6s. But anyways, yeah, I'm writing n instead of pi. But yeah, so I'm going to erase that down there, but you can figure that out. I'm going to erase this.
Oh, I was trying to copy that part. Yeah.
But we're gonna make our x-axis all radian angles of pi. Actually, speaking of pi, what is the domain for this, do you suspect, before we graph it? What are the possible x values? Are there any limitations on what I could plug in for x? Does pi accept a negative angle? Right? A negative angle, you could find a coterminal angle by adding 360 a certain number of times to it. It turns out the domain is going to accept anything. The range is going to be the set of all y such that -1 is less than or equal to y is less than or equal to 1, because we talked about that earlier. That y only gives us values between those. Well, let's start plotting some points. Plotting points. So let's see. We've got the origin. What was sine at pi over 6? 1/2. So up here at 0.5, roughly. Roughly exactly. Okay. Does anyone have any predictions on what this is going to look like?
It's going to be boom, boom.
Boom, boom.
Yeah.
Something like that. Okay, we'll see. Pi over 4 is equal to root 2 over 2. Pi over 4 occurred right here. All right. Root 2 over 2 is 0.707-ish. So here's 0.7. So root 2 over 2 is right here. We'll see. We'll see.
I got $1 and cent.
Pi over 3 is root 3 over 2. That's 0.866-ish. Is that a straight line? No, I don't think. It's not straight.
Maybe because your dots are off.
Maybe, we'll see. Sine of pi over 2 is 1. So pi over 2, all the way up here at 1.
It's making a...
Yeah, that doesn't look like I can't draw a straight line that would hit those. And then sine of 2 pi over 3 is root 3 over 2. So that's dropping back down.
Still making a mountain, though, so I don't know.
And then dropping back down, and dropping back down, and dropping back down.
Now go to Excel now, do it.
Well, I'll do it in Geometry Sketchpad in a moment. So this isn't a sharp angle. It turns out this is actually going to be a smooth curve.
Parabola.
Not quite a parabola.
Oh, you did good, Alex.
Yeah, that's all right. 5 pi over 6 threw me out.
Just make that dot bigger.
And now, Sam, you just said something interesting. You said it was going to drop down.
Yeah, so then it goes into the negative coordinate.
Right, because sine was positive for quadrant 1 and 2, right? Quadrant 1 was here. Quadrant 2, I guess I'm labeling that funny, it was between pi over 2, 90 degrees and 180, right? And now I'm entering into quadrant 3 and quadrant 4. So it's actually going to repeat these same numbers, it's just they're all going to be negative. Okay, so sine of 7 pi over 6, the reference angle is pi over 6, but it's negative, so it'll be negative 1/2 at that point. Okay, sine of 4, well, I guess I'll do the, what would that be? 5 pi over 4 would be right here, would be down at negative 0.707. And then negative, oh, I did that in the wrong spot. That's right here.
Mr. One.
And then negative 0.866. And then sine of 3 pi over 2 is negative 1. Where's 3 pi over 2 in terms of degrees?
Good question.
Where's pi in terms of... Pi is 180, right? So what was pi over 2?
It's 270.
Pi over 2 is half of 180, so that's 90. So 3 pi's over 2
270.
would be 270. And at 270 degrees on the unit circle, what is sine equal to at 270?
90. Negative 90.
No.
You use the reference angle?
Well, sine was equal to the y-coordinate on the unit circle. So imagining at 270 degrees all the way over here, what was the y-coordinate on the unit circle? -1. And notice that is what I got here. So just trying to make as many connections as I can for you guys. And then it's going to go back up. Back it up. Back it up. Back it up. And at 2 pi, it's at 0
It's going to do
again.
the exact same thing. So we're repeating like that, right?
Yeah, and if I wanted to figure out what is sine of 13 pi over 6, that is bigger than one circle, that would be a reference angle of pi over 6, and it'd be at a half. So it would actually repeat, it would repeat this pattern in both directions infinitely. In fact, I think I can show this to you on this. Let's see. I gotta shrink this down here. Whoa. All right, so here's my computer metric graph. If I graph the sine function, notice that's what I get. So here's 2 pi, here's 0 pi, pi over 3. It's hitting its maximum height at pi over 2, or 90 degrees. It's hitting its lowest height at 3 pi over 2, or 270 degrees. And watch this. And actually, if I
there's the mountains.
regraph it, you can see that it's repeated. And how often does it repeat?
Forever.
It repeats forever, but what would the period of this graph be? 180 degrees? If it was that, then it would be up and up and up and up.
360.
360 degrees is what it takes to go through one full cycle, right? And actually, not only does it do it in that direction, but it also does it for negative angles. So it wham, 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 right? So it ends up doing this in both directions infinitely, and its highest value is +1, its lowest value is -1. All right?
Heartbeat monitor.
And I want to point out that these arcs are not circles, they're not circular, and they're actually also not parabolic. But yeah, so some interesting results for sine.
Then make that cosine.
Cosine?
Yeah, make that cosine.
Should we do a table of value for cosine?
Yes, we should.
Well, actually, let me ask you some other questions on sine first. So the domain is everything. That makes sense. It goes from -infinity to +infinity. The range goes from -1 to +1. Let's see. What is the y-intercept? What was the y-intercept on this graph? 0 is the y-intercept right here.
And pi.
And where do x-intercepts occur? X-intercept occurred at 0. It occurred at pi. It occurred at 2
It's going to
pi.
be at 3 pi next, right?
So it occurs at values of pi times n, where
So-
n is any
The
number.
next pi would be 3 pi. The next x-intercept be 3
I
pi.
don't think, no, it can't be any number, because like, what about 1?
Or n is an element of the integers. Let's see. I think
Integers.
z is this weird
Oh.
double z is the notation for integers. But n is an element of the integer, so n is an integer is the way I'll write it for you guys. Where do the maximum values occur?
180.
The maximum value occurred where?
90 degrees. 90.
90 degrees, or at pi over 2. So at pi over 2 it occurs, and where else would it occur?
3 pi over 2.
It would occur a full, how far away from that?
1 period.
1 period or 2 pi units away, right? So the maximum values occur at pi over 2 plus 2 pi, plus or minus, I guess, if I wanted, and 2 pi times n, where n is any integer. So if n was negative, if I go back a full 2 pi, I'm at another maximum value. If I go back 4 pi, or 8 pi, or 26 pi, as long as it's an even number of pi's, I'm good. And that will land me on a max. Where does the minimum occur? 270, or 3 pi over 2, right? And where else would that occur?
2 pi n.
Plus 2 pi n, where n is any number. So if I go subtract 2 pi from this, there will be a negative, a minimum value over there at -1. If I add 2 pi to that, there will be a positive value way over there at, 3 pi over 2, right, plus 2 pi. Be way over there. Also at the height of -1. So all sorts of interesting things here. So what about cosine? What about cosine? How do you think that would be different from sine? Would cosine have the same period as sine?
Yes.
Yes, because it follows the same cycle from 0 to 2 pi. Except cosine is going to be positive and negative in different locations.
Won't they just be switched?
Just switched? So like flipped?
No.
No.
Maybe it goes positive, negative, negative.
And what's the value of cosine at 0? Does anyone know?
1.
Cosine is 1. So the graph of cosine, it's shifted.
Uh-oh.
Interesting results.
Whoa.
So there's the graph of cosine of x. It's just off by, do you know how far off that is? What's it shifted by? 90 degrees off, which is, that's one full quadrant off, isn't
About a
it?
tangent.
Oh, we're not ready for tangent yet.
We're not.
No. We're just doing sine and cosine today.
Still. Snail.
All right. So for some of your work tonight, you'll end up having to know, some of the facts about cosine, knowing where the maximums and the minimums occur and stuff like that, recognizing periodic functions and stuff. So cosine has its max and mins occur at different locations, but it still has the same period, right? Notice that from this maximum all the way to this maximum is 2 pi units. Okay? And they're pi over 2 units apart from being the same. All right, so it turns out actually that there is a relationship between sine and cosine where I think sine is equal to like cosine minus pi over 2 or something like that. But nonetheless, that's all we have time for today. We're going to do more with this later where you can change the period of it. You can change the height of it later on. And we'll end up being able to use this to model things like lunar cycles, tidal cycles, temperature cycles perhaps, and different things like that.
So what are the questions that you like?
We'll see in just a minute. But goodbye, Internet.